Last time we talked about some new concepts about the conditional probabilities, right? And then we derived some of the equations that might be useful for our future derivations. Um, and we reached this quite important equation, which is called Bayes theorem, right? Um, so the conditional probability of y conditional on x equals to uh, the probability of x conditional on y times the marginal of y divided by the marginal of x, right? So this is purely just a mathematical derivation. So um, um, it's based upon these two equations, right? So the definition for x conditional on y, the probability of x conditional on y equals to the joint probability divided by the marginal of y, right? And then the conditional probability of y conditional on x equals to joint probability divided by marginal on x, right? And then if we multiply hy on both sides of this equation and gx on both sides of this equation, we get this this equality. And then this is so this equality can be simplified to this equality, and then we simply just divide gx on both sides of the equation. In order to understand the importance of the Bayesian theorem, we need to attach some specific meanings to this particular equation. The equation was derived upon by assuming a continuous sample space, right? But if the sample space is discrete, we can write the Bayes theorem in this particular form. So the probability of y conditional on x equals to the probability of x conditional on y times the margin of y divided by the margin of x, right? So how do we actually attach some specific meanings to those symbols, right? So in the context of machine learning, usually we use x to represent data, observations, right? We use x to represent observations or data, right? Those things that's provided to us, those measurements, those observations or those samples that's actually provided to us, right? And then y is usually used to represent so-called hypothesis or model. So a hypothesis is just a simplified model, right? But usually y can be used to represent a certain kind of model, right? Later on we are going to look at some examples, right? So this equation actually tells us how do we actually calculate the probability of our model given a certain set of observations or a certain set of data, right? And the formula tells us how do we actually compute that. We can compute that by using the so-called likelihood of the model given the data, right? So if you look at this conditional probability as a function of model y instead of as the conditional probability of x, here we are assuming that the observation or data is given, right? Then it becomes a function of y. That's the model, right? So we call it a likelihood, right? The likelihood of the model times the prior of the model, right? It's the probability of y alone. That's the model alone. That's actually the marginal probability of y, right? And then divided by the marginal probability of x. That's the probability of the observation, right? Or the data. So if you actually understand Bayes' theorem in this kind of context, this equation becomes particularly useful for us to decide or making decisions or coming up with a computable formula for machines to make decisions. One of the questions that students have been asking me is how do we exactly compute the denominator, right? How you actually compute the denominator? In practice, this denominator doesn't have to be computed usually because the denominator doesn't depend upon the model y, right? So when we actually implement the machine learning algorithms, we are usually comparing the probabilities of competing models or competing hypotheses, right? And this denominator doesn't depend upon the model y, right? So usually, if we are just doing this kind of comparison, it's enough to actually compare the numerator in order to actually decide which model actually has a larger posterior probability, right, given a certain set of data, right? But in order to actually do some of the exercises, we do need to understand how the denominator was actually computed, right? So for the continuous case, uh, the margin of x equals to the joint probability integrated over y, right? So that's the definition of the marginal. If you still remember, right? We just integrate the joint probability over y, and then we get a function of x. That's the marginal of x, right? And then we know that if we integrate the marginal of x again with respect to x, then we should be able to actually get 1. Here we are just using this particular definition of the margin of x, right? And then what's actually the joint probability of fxy, right? fxy equals to px conditional on y times hy, right? So you just bring it in there, px conditional on y times hy, and then integrate over y, right? And this is for the continuous case. For the discrete case, you can just replace the integrals with the summations, right? So the probability of x conditional on y times the margin of y, right, and then sum over all the different values of y over the entire sample space for y, basically, right? So that's gonna allow us to actually compute the denominator, right? Now let's look at a specific example which is actually related to medical diagnosis, right? And this is actually a realistic scenario, and it's an example that's used quite widely in textbooks and other education materials and also other YouTube videos. The scenario is like this. So the doctor suspects that you have acquired a very rare form of some kind of disease, right? And he's suggesting you to actually take some tests. And he's telling you that the accuracy of the test is 99%. So what does that actually mean, right? What does it actually mean? 99%, it means what? It means if you have the disease, so the hypothesis is that y equals to sick, so you have the disease, right? That's the hypothesis, right? If you have the disease, and the chance that the test is going to return a positive result is going to be 0.99. That's 99%. If it's the other kind of scenario, if you don't have the disease, let's say that you are healthy, right? Not having the disease doesn't equal to being healthy, right? But here we actually just assuming that not having the disease is kind of the same as healthy, right? So, and then the result is negative. The test result is negative, is also 99%, right? And then what you are concerned about is that what you want to know is that given that the test result is positive for you, what's actually the probability that you are actually sick? You actually have the disease, right? This hypothesis that you are sick is actually true. You want to know that. You want to know that, right? Suppose you go to the test lab and did the test, and the result becomes the result is positive, and you want to know what's actually the probability that you actually have the disease, right? So how do we actually compute that based upon the Bayes theorem, right? How do we actually compute that? So the Bayes theorem tells us that y conditional on x equals to the probability of y conditional on x equals to, right? We just take this equation, the conditional probability of x conditional on y times pry, right? X equals to positive, y equals to sick, positive conditional on sick, right? Times pry, y equals to sick, right? And then the denominator is prx. Prx is x equals positive, right? And then we can just bring some numbers back in here, right? If the hypothesis is that you are sick, and then the test result is positive, the probability of that, the conditional probability of that is 0.99, right? And then what's actually the prior probability for you to actually have the disease, for the hypothesis to be true, right? It's actually quite small. The prior for you to be sick to actually have the disease is 0.001, right? That's the prior that's given to you. So out of 1,000 people, there's only one person that could have the disease, right? It's a very small probability. It's a very rare form of the disease, right? So you can actually stick this number in there, right? And then what's gonna be the denominator, right? What's gonna be the denominator? So PRX equals to positive. And here we have to actually use the equation that we just derived. PRX equals to positive equals to PRX equals to positive, and then conditional on Y, right? And then multiply on margin of Y, and then you sum over all the different possible values of Y. We only have like two hypotheses. One is Y equals to positive, and the other one is Y equals to one is Y equals to sick, and then the other one is Y equals to healthy, right? So we have to actually account for both probabilities, both kinds of possibilities, right? So PR X equals to positive, conditional on Y equals to sick, times PR Y equals to sick, plus PR X equals to positive, conditional on Y equals to healthy, times PR Y equals to healthy, right? And that's exactly what I'm writing here. PR X equals to positive, conditional on Y equals to sick, times PR Y equals to sick, plus PR X equals to positive and Y equals to healthy, times PR Y equals to healthy, right? But how do we actually get those numbers in there? How do we actually get those numbers, right? So the first number is kind of quite easy, right? PR positive, Y equals to 6, that's 0.99 times the prior, that's 1 out of 1,000, right? 1 over 1,000. And then what's going to be the next term in the summation, right? What's actually X equals to positive and Y equals to healthy, right? So X equals to positive, Y equals to healthy is actually 0.01. How do I know that, right? Because I know what's given to me is that if you are healthy and then the test result is negative, it's gonna the chance is 0.99. That's the 99% of probability, right? And I know that the conditional probability should return a summation over X equals to 1, right? So if I actually look back at one of my equations, that's this equation, right? It's the conditional probability integrated over Y. That's the conditional probability of X conditional on Y integrated over X. Integrate X should give me 1, right? So for a given Y, the probability of X equal to 6 plus X equals to X equals to positive plus X equals to a negative conditional on the same Y should give me 1, right? If you change the integral to summation, that's exactly this number here, right? So Y equals to healthy, right? If X equals to negative is 0.99 probability, right? And then these two numbers should add up to 1, right? So if Y equals to healthy but X equals to positive, the test was wrong, right? The test was wrong in this particular case. And then the possibility is actually 0.01, right? And then I can stick those numbers in there, right? And then I can actually carry out my calculation and then get the denominator, which is actually 0.01098, right? And then I can actually carry out this division here, and then I obtain a result that's like 0.0902. That's about 9%, right? So even though the test result is positive and the test is 99% accurate, I only have like 9%. It's less than 10% of chance to actually have the disease based upon this particular positive test result, right? But how do we actually understand this particular test result, right? I have like less than 10% of chance to actually have the disease given the test result is positive, right? How do I actually understand that? Suppose I have 1,000 people. Right? And then out of those 1,000 people, I only have like one person that could have the disease. That's only one person that could be sort of have the disease, right? Suppose the test results is positive for that person, right? So we have one positive test result, right? But if we apply the same test to the remaining 999 person, right? To the remaining 999 healthy people, right? There's 1% of a chance that the test could be wrong, right? For those 999 healthy person, right? So I could still get like a 9 or 10 people that's positive, that have a positive test result, but nevertheless they are actually healthy, right? So that's how many positive test results. I have like 10 or 11 positive test results, right, out of these 1,000 people, but only one of them actually has a disease. So 1 over 10 or 1 over 11, that's about 9%, right? 9 or 10%. So this is some kind of a counterintuitive results, but it has very very important consequences for us to understand the Bayesian theorem. So what if I want to get a second opinion after I obtain the positive test result for my first from my first doctor, right? So suppose the second test you are getting is still positive, right? What's going to be the posterior probability that you are actually sick, right? So the most important thing about the second test is that it has to be independent from the first test. So if your first doctor is using a certain lab, right, and then if you want your second test to be truly independent, you have to make sure that your second test from your second doctor or a different doctor has to be from a second from a entirely different lab, right? Um, the calculations are going to be quite similar. It's going to be exactly the same actually, right? Except that you have to change two numbers. Um, you have to change these two numbers basically. So for your second calculation, if the test result is still positive, you have to change the prior. The prior for your hypothesis that you are actually sick, right? So for the first calculation, the prior that you are actually sick is 1 over 1,000, right? But for the second test, if it's independent, you will have to be you have to sort of use the posterior of your previous calculation, which is actually 9%, to replace the 1 over 1,000. So for the second test, the probability of the prior probability that you are actually sick should be replaced to 0.0902, right? And then the corresponding probability that you are actually healthy, that's the opposite hypothesis or alternative hypothesis, right, is supposed to be 1 subtract this number, right? That's like a 0.9098, right? And then all the rest of the calculations has to be will be identical, So it's a so that's the numerator, right? Numerator, you replace the 1 over 1,000 with 0.0902, right? And then when you compute the denominator, right, you have to actually change PRY equal to 6 from 1 over 1,000 to 0.0902, right? And then plus uh, this number is y equals to healthy. That also changed accordingly, right? And then that's the value of the denominator, right? And then if you bring this denominator into the calculation, that's gonna be you're gonna get a result that's about 0.9075. So that turns out to be like 91% of chance that you are actually sick, right? So if you are still not convinced, you take a third independent test, right? And then for the third calculation, you're going to have to use this 91% as the prior for the third calculation, and then repeat the calculation again, and that's going to give you an even higher probability, right? Um, so that's how you can actually use the Bayesian statistics to understand this specific example, right? The result of this calculation may have practical implications, how you can actually use it to understand medical diagnosis, right? And understand test results, right? But the most important thing for our purpose is to actually understand um, the specific meaning that's attached to the two different random variables, x and y, right? So here, x is actually the test results. That's the data. That's the observation, right? And then y is actually the hypothesis. And in this particular example, in this specific example, we have two different hypotheses. One is that you are sick, you got the disease. The other one is that you are healthy, you don't have the disease, right? And then for the data, we also have two observations, two possible observations, right? And one is positive, the other one is negative, right? Test result could be positive, test result could be negative, right? So both sample space for x and y are discrete, right? And then we only have like two different values for the two different sample spaces. Yeah, that's our first example to illustrate Bayesian theorem, Bayes theorem.